A very good day to everyone. So I am Syasya, binti Ong Amat. So today I'm going to present my final year project titled Development of Polyvinylidene Fluoride Membrane via Assembly of Tannin Acid and Polyvinyl Pyrrolidone for Filtration of Oil Water Emulsion. So first of all, this is the outline of my presentation, where first I will start with the introduction, then the problem statement, objective, hypothesis, literature review, methodology, results and discussion, and lastly with the conclusion and recommendation. So without further ado, I will start with the introduction. So as we all know, with the rapidly increasing industry's development, the amount of oily wastewater produced will also be increasing. So with this increasing amount of oil water, the amount of discharge to the environment will also be increasing. So what we want to achieve here is treated oily waste. But why is it important? So discharging oily waste to the environment could lead to many bad consequences, such as affecting our groundwater resources, our aquatic livings, our drinking sources, and also our health. So most of the oily waste produced is in the form of oil water emulsion, where it is the most challenging form of oily wastewater. So this is because it is very stable due to its low interfacial tension, and also it has oil particle size which is lower than 20 micrometer. So many technologies have been invented in order to treat this oily wastewater, but not many is invented to treat oil water emulsion. Some of the technologies invented includes flotation, biochemical, coagulation, and many others. But these technologies have their drawbacks, such as expensive, it uses toxic compounds, and also it requires a large space of installation. So membrane technology is one of the alternatives that we can use, which it is environmental friendly, it is easy to customize, and also it is very cost effective. So PVDF is one of the most popular material used in fabrication of membrane due to its good mechanical properties, excellent chemical stability, and also good pore properties. But PVDF polymer is hydrophobic, which I will explain further later. So moving on, as you can see, here is the simple illustration on how membrane works in separation of oil water. So the principle is quite simple. So the membrane acts as a specific filter, which is only allow water to flow through it, and then the suspended oil particles will be catch. So moving on to the next diagram, so we can see that the particles deposited on the membrane surface. So this is one limitation of membrane, where its performance would reduce over time due to membrane fouling. So membrane fouling is when the particles deposited on the membrane surface or the membrane pores, as shown in the diagram. So when the pores are blocked, less permeability will be produced, thus reducing the membrane performance. So as I have mentioned before, PVDF membrane is a hydrophobic membrane. So the filtration of oil water by using PVDF membrane will easily fool the membrane, as the oil particles will plug on the surface, resulting in small filtration and high energy consumption. But however, membrane can be modified in order to improve its fouling properties, which is what we want to achieve in this research. So one of the widely used methods for surface modification of PVDF membrane is by phase inversion, where the polymer in liquid phase is transformed to a solid phase, as shown in this diagram. So this method is widely used because it is very simple and it does not consume much time. But fabrication of PVDF membrane alone will produce a hydrophobic membrane. So in order to improve its hydrophilicity, what we can do is by adding hydrophilic additives. But addition of hydrophilic additives will also produce hydrophilic membrane due to leaching, where the additive is washed away due to its hydrophilic properties. So a new methods are required to fabricate hydrophilic PVDF-based membrane. So this is the problem statements of the research, which is first, oil water emulsion is a challenge to treat, and then membrane process is attractive but faces problem of membrane fouling. So PVDF membrane is attractive but suffer from low flux and severe fouling, and then modification of PVDF membrane via blending with hydrophilic additives leads to hydrophobic membrane due to additives leaching. So moving on to the objective, what we want to achieve is to develop PVDF-based membrane for effective separation of oil water emulsion. So for this, first we need to fabricate and characterize PVDF based membrane by incorporating assembly of TA PVP in the membrane matrix. Then we want to evaluate and filtrate the filtration performance of the developed membrane in separation of all water emulsion in terms of permeability and rejection, and then to assess the anti-fouling properties of the developed membrane via multiple filtration tests. So many modification development of PVDF membrane for all water emulsion has been reported. So it is summarized in this table. So as we can see, every modified membrane has improved hydrophilicity indicated by the low value of the water contact angle and high flux produced. So through this also, the fouling resistant propensity for all water emulsion separation are also improved. But however, some drawbacks is identified, such as harsh fabrication condition and also unstable and poorly distributed coating layer. So with that, a new method is proposed. So now I'm going to talk about the fabrication done in this research. So in this study, to produce the hydrophilic PVDF membrane, formation of TA, PVP and iron 3+ assembly is fixed into the membrane via in situ complexation reaction during the membrane fabrication. So TA is an innovative additive to improve the hydrophilicity of membrane, offering a wide range of interaction with other materials. So while PVP is used as a poor performing agent, which it has good compatibility with TA through hydrogen bonding. So the coating of TA and PVP imparts binding sites, which allows the capture of metal ions through coordination reaction to form complex and immobilize the coating in the membrane. Shown in the diagram, as we can see here, where the blue component is represented by PVP, the black one is the TA, and the orange component is iron 3+. So as you can see here, they form complexation, which will fix the TA and PVP into the membrane matrix. So moving on, I'm going to explain the methodology. So this is the flow in conducting this project, where first I start with the literature review and then come out with the problem statement and formulation of hypothesis, and then come out with the membrane fabrication and then membrane characterization and performance test, which here is the list of membrane characterization and membrane filtration test form. And with the data collection, we proceed with data analysis and report preparation. So for the membrane fabrication, so as you can see here, as I have mentioned before, the fabrication is done through phase inversion. So phase inversion basically is conducted in 4 steps, which is first, the material for the membrane are mixed in a reagent bottles and stirred continuously to produce a polymer solution. And then the polymer solution are left cool and make sure there are no bubbles formed. And then the polymer solution is cast into a thin film on a non-woven support and exposed for a while to the atmosphere, which is then it will be immersed into the coagulation bath to transform the liquid into solid. So moving on, there are 4 different membranes studied, which are different in the composition of the polymer solution and also the coagulation bath used. So the first one is PVDF membrane M1, and then the second one is the modified PVDF membrane with TA and PVP as the hydrophilic additives. And then the third one is the complex PVDF membrane with TA and PVP as the hydrophilic additives, and 0.001 molar of iron solution is used. And then the last one is M4, where we also use TA and PVP as the hydrophilic additives, but the coagulation bath is 0.05 mole of iron solution. And then below is the setup illustration on how of the filtration test, where first the feed is formed into the membrane and the volume of the permeate produced is collected. So this is the actual image of the experimental setup, and this is the parameter used, where we use membrane area of 2.24 cm², and then the transmembrane pressure of 0.2 bar. The feed used is 1 ml per liter crude oil in water emulsion. So moving on for the results and discussion, first for the membrane morphology. So from the figure, we can see that the pristine PVDF membrane has a smooth surface with homogeneous pore distribution, and the addition of TA and PVP additives to the membrane M2, M3 and M4 demonstrate obvious change to the amount and the size of the pores produced on the membrane surface. So the pore size of M2, M3 and M4 is slightly increasing, which indicates that the TA and PVP is successfully incorporated to the PVDF matrix. So the presence of iron 3+ in M3 and M4 gives a more compact pore distribution to the membrane compared to M2. So this could explain that the ability of TA, which imparts binding sites to form a cross-linking reaction with PVP and iron 3+, thus form a more compact membrane in M3 and M4. While for the pore distribution, so as we can see, the addition of TA PVP into the solution increases the mean pore size of the membrane compared to M1. So this is due to the addition of the additive PVP as a pore performing agent, where it is able to migrate during the phase inversion due to its good hydrophilicity, thus performing the pores. So also the usage of iron 3+ reduced the pore size as shown in M3 and M4 compared to M2, which justifies the ability of TA and PVP to form complex with iron 3+. Next, moving on to the ADX analysis. So from this ADX mapping, distribution of CF, N and O element in M1 had a significant change compared to the rest. So the relative amount of C and F is slightly reduced compared to the PVDF membrane. This is due to the retention of TA and PVP into the membrane matrix. So from the EDX composition analysis also, it is observed that there is increasing in the percentage oxygen element in M2, M3 and M4, which justifies the successful incorporation of additive TA, which is very rich in O element into the membrane matrix, while the abundance of N, shown here, is attributed to the presence of the PVP. Next, moving on to the FTIR analysis, we can see that new peaks are formed at 1637 for the modified membrane, which is attributes to the C+O stretching vibration, which was derived from the complexation of TA and PVP. While for the XPS analysis, we can see that comparing to M3 and M4, which is different in the coagulation values, we can see that M3 has higher oxygen peak, showing more O elements than M2. So this indicates that the complexation reaction results in a higher retention of TA and PVP, and also it indicates that the degree of the additive leaching is reduced via the assembly. And then moving on, as for the surface contact angle, the water contact angle for the modified membrane M2 and M3 is improved, indicating that they improve in the hydrophilicity properties. So the ability to form coordination reaction between TA and iron 3+ results in the lowest water contact angle in M3, but higher concentration of iron solution used in M4 was contradicting with the results in M3, which might be due to the higher complexation reaction rate between the additives, thus residing the hydrophilic additives in the inner layer of the membrane, thus showing a higher water contact angle. And also for the clean water permeability, as a result of the improved hydrophilicity properties and the increasing pore size, the clean water permeability increases for M2 and M3, but reducing for M4 as mentioned before due to the additives residing in the inner layer of the membrane called swelling effect. And then moving on to the permeance recovery analysis. So as we can see here, the membrane undergo 5 cycles of all water emulsion filtration, and flushing of membrane was done after every cycle ended. So in this all water emulsion filtration, so M3 shows the highest permeability, which supports the hypothesis proposed, which was with the increasing hydrophilicity of the membrane, the falling effect could be reduced, thus resulting in higher permeability. While M4 shows the most stable permeability rate from falling, where the permeability was almost constant after the second cycle. So this also supports the argument on the swelling effect on this membrane. Comparing to M1, so this membrane shows a significant decline of permeability due to its hydrophobic properties. And then moving on, for the falling resistance analysis, So every modified membrane M2, M3 and M4 shows improved falling properties compared to M1. So this is as the result of the increasing hydrophilicity. So for this discussion, we are going to compare M1 and M4, which is in the low permeability regime, and also M2 and M3 at the higher permeability regime. So as we can see, due to its low permeability, it will also produce low falling rate. So as we can see, as the improved hydrophilicity of M4, it produces lower falling rate, and comparing to these two, due to its higher permeability, so it will also have a higher falling rate. So this is because the pollen is trapped by the flow of the permeate. As you can see, as a result of the higher hydrophilicity in M3, it will also result in lower falling rate compared to M2. And on the last part of the result is for the oil rejection performance of the membrane. So from the figure, we can see that every modified membrane shows improved rejection performance by more than 80% compared to M1. So this shows that the improved hydrophilicity properties of the membrane enhance the oil particle rejection. So as we can see, M4 shows the highest rejection percentage of 90%, which is the highest compared to the others. So this proves the hydrophilicity of M4, although membrane shows high value of water contact angle in the contact angle analysis, and it justifies the swelling effect of the membrane. So in conclusion, I can say that the in situ formation of TA-PVP assembly aided by the iron 3+ is effective in enhancing the membrane properties and the all water filtration performance of the PVDF membrane. So as we can see from the results shown by M3, the incorporation of the TA-PVP assembly with the complexation offers enhanced surface hydrophilicity, enhanced clean water permeability, which is 4 times faster than the pristine PVDF membrane. It also shows enhanced oil water filtration permeability, with which is 3 times higher than the pristine PVDF, and also enhanced oil rejection performance and anti-fouling propensity. So as for the recommendation, so the overall performance can still be enhanced because the optimum membrane chosen, which is M3, still suffer for 30% loss from its extreme potential. So more study can be done in order to improve its anti-fouling propensity. So this is the references used, and that's all from me. Thank you.